on the basis of race. Okay, so those are the only two federal laws, and otherwise states are allowed to adopt their own criteria. In Michigan, we have a subset of, or a set of criteria that are applied. The one that's the most interesting for this data set is that it says the districts shall be reasonably compact, okay? In many other states also have this reasonably compact requirement, but most of them don't give any definition for that phrase, okay? So there's a data set where you know, some social scientists at Harvard said, let's figure out what people think is reasonably compact. And we're going to show people a collection of districts and ask them to tell us which ones are more and less compact, okay? So on the next coming slides, I'd like to take a poll for the audience to decide what they think is more or less compact. Remember, that's the only definition, the word compact. I'm not telling you what it means. And hopefully also I can get a volunteer in some of these slides to tell me why they made their choice. So remind me, how should I try to get the volunteer again? Just ask and look for a hand raise, is that right?
Right, so any volunteer can simply raise his hand. So if you go to the participants menu, you'll have a raise hand button in the bottom. And you can raise your hand, and then I will ask you to unmute, and you can unmute your mic, and you can talk. Great.
So I hope we get some volunteers. Okay, so all of these districts are United States districts. So here are two images. You can see they made the images as sort of plain as possible, just black and white. So let's take a poll starting on this slide. So we also have this polling option. Which one do you think is more compact, A or B? And then if someone can tell me what why they made their choice, I would be happy to have a volunteer. I can't see everyone, so I don't know.
We have a volunteer.
Great.
I think, Mario, you are unmuted.
Yes.
Hello.
Hello. Hi, Laura.
Hi.
So I would say that B is more compact because it's sort of more, let's say, less non-convex.
Right, less non-convex. Okay, great. That is a very common response on this pair. All right, so let's go to the next one. Which one of these is more compact? Why would you select that? Can I have another volunteer, please?
So here we have Sebastian.
Great.
Sebastian.
Forcing people to pay attention.
You have to unmute him.
Yes.
Hello. Yes, I think it's A. Because I'm looking at this like the area is close to the center point.
Mm-hmm.
Like as close to a circle as possible. So
Yeah. Very good. Very good. Okay, great. So let's just do one more. We'll take one more volunteer. If you could tell me which one on this one it looks more compact to you.
Okay, we have another volunteer, João.
Okay. In this case, I believe I'd still pick B because the area of A seems to be more sparsely positioned compared to the center point.
Great.
Following up on Sebastian's answer.
Right, great. That's good. And just to make a side comment, in the state of Michigan, actually, we're one of the only states that gives some explicit outline and definition of what you might be interested in, using as a metric for compactness. And one of them is like basically as close to a circle or square as possible. And you can measure something like that using the center of mass and the way the mass is distributed around that center. So, okay, we have two more. How about you just fill out the poll for these and tell me which ones you think are more compact. So this is pair number 4. Okay, and then pair number 5. Which one here is more compact? This might be more challenging. Okay, so we've had 5 different pairs. I want to point out that for each one, when I asked the 3 volunteers, like, why were they choosing that particular district to be more compact, there was really a dominant feature, a dominant characteristic of that pair of districts that encouraged you to make a particular decision, okay? So here's some of the results from the real data. I don't know, do we show, is there a way to show the results of the poll, or? You know what, let's not worry about it, but I'd be very interested to see the results later, and then I can email you and you can share with everyone how accurate, or let's say, oh, there we go.
Am I doing it?
Yeah, I see it. Yeah, okay, cool. Okay, so A, B, and C came from pair number 2, 3, and 5. So 2, everyone, or people agreed from this audience, 88% agreed A is more compact than B, whereas in the data, 70% felt that way. And then in pair number 3, in the same way, it's lined up. So 90% of the data set thought that the right-hand one was more compact than the left, and in our data, 83% thought. But then for pair number 5, yeah, you can see in the data, A was more compact than C 60% of the time. In our case, it wasn't flipped, meaning A more than, right, meaning A more than C. In the case of the poll, A more than B. I'll fix that the next time I give the talk to make it clearer. But you can see it's much closer, right? 42% of you thought the left one was more compact, and 58 on the right. And so it was much harder to decide in the context of pair number 5, which one was more compact. Okay, so you can see from this example how intransitivity might arise in these data, okay? And in particular, like I said, you talked about certain features that you were looking at with a given pair, okay? And in the paper where they collected these data, they actually collected a lot of pairwise comparisons, and they found that it was extremely hard to model from these pairwise comparisons. And so their conclusion was that this pairwise approach enables respondents, or the audience in this case, to make each paired comparison independently, and may encourage them to use different dimensions for different comparisons or different features in machine learning language. And that really is very natural. I think it's natural to see why that happens in the pairwise comparison context. In their case, because of that modeling issue, they actually just stopped using pairwise comparisons and started asking people to rank many items. In fact, in the one case, they were asking respondents to rank 100 districts. So they were paying them, fortunately, but they had to go through and say, okay, which one is more compact from the most to the least. So what we want to do, instead of just abandoning pairwise comparisons or small k-wise comparisons, is try to model exactly the behavior that they considered happening by the respondents in these pairwise comparisons. Okay, so we want to model the fact that some features of these pairs are salient in the context of that pair that may not be salient when you look at the entire collection of districts. Okay. Okay, so just one more illustration. We want to ask, how do we respond? Is there a model for how we respond? In this case, where we're doing pairwise comparisons versus when we see all of them at once. Okay, so let me tell you exactly how we model that. First, just with a picture, okay? So we base our model on a very common and simple model, which is called the Bradley-Terry-Luce model. And here's an illustration of Bradley-Terry-Luce, or BTL, in 2 dimensions. So every purple dot is an item in our data set, like a shoe. And in this case, we only have 2 features for each one of those items. And Bradley-Terry-Luce assumes that there's also a judgment vector in the feature space, in this case in the 2-dimensional space. And the direction of that judgment vector, you can say the entry of that judgment vector in each coordinate basically dictates how important that feature is for making whatever comparison that you're trying to make, like how important feature X is for comfort, and how important feature Y is for comfort, if we're using the shoe example. Okay, so then with these items in the same space as the judgment vector, you can see that if you just project the items onto that judgment vector, or take the inner product of the item vector with the judgment vector, you'll get scores for each item. And BTL says that the items with the higher scores will win a pairwise comparison with a higher probability. And that probability depends on the difference in scores. So in this case, item 2 will, when compared with item 3, will win with a very high probability. Okay. So what we introduced was an idea of salient features, which is just projecting onto feature axes. Okay, in this case, I'm just illustrating projecting onto one axis or one coordinate or the other, but in higher dimensions, you can project onto a subset of the coordinates. So if we first project our items onto one of these axes, you can see then the ordering with respect to the true judgment vector will be different. Okay, and in particular, if this is the behavior that happens, it results in intransitivity. Okay, so consider the triple 4, 2, 5 in this case. If the pair 4 and 2 only uses feature Y, so only uses the right-hand plot, then 4 beats 2, at least with a high probability. And if pair 2, 5 only uses feature X, then 2 beats 5. Okay, but there are 2 cases where 4 beats 5, either if it uses X or if it uses both features. And so then 5 beats 4, and we have an intransitive cycle. Okay, so it makes sense that if you're only considering some subset of the features and using still the same judgment vector, that you'll result in some intransitivity. And this is exactly the way that we model our respondents' answers in our mathematical model. There's a lot of related work on this, areas, even specifically the violation of rational choice. And several social science papers have commented on what we're calling the salient feature phenomenon. So, that was really a motivation for us. In all those papers, they weren't trying to model or learn from data. They were just trying to recognize the actual behavior that's happening. But that motivated us, that they really felt that was an extremely relevant characteristic of the data. And then there's people in machine learning, the second bullet here, who have also tried to model the utility of each item as a context-dependent utility. And some of them like learn features or assume features the way we do, and then use methods, similar to ours, or neural networks in order to try to learn those context-dependent utilities. Okay. But our work, different from all of these, is that we do the following simultaneously. So first of all, we have a convex model that results in intransitivity, which none of the other approaches have. And whether a convex model is the right thing to do, I won't have a debate about that. I don't know. I work on non-convex models regularly, but at least we know that we can solve it to the minimizer of the likelihood, of the negative likelihood. And then, like I said, we have this foundation in social choice theory motivating our approach. We can generalize to unseen items and pairs. In part, that's because we assume we know the features of the items. And so if you give me a new item with new features, I can generalize. And I can learn from intransitive pairwise preferences. I can learn a complete ranking of all the items. And that's another thing that's unique to our work. And we also have complexity guarantees that I'll tell you about in the second part of the talk. Okay. All right, so now we have the first part with introducing our model. Okay, so here are the notational preliminaries and items, each one with a feature vector in d dimensions. So we have a d by n matrix. We assume some judgment weights, W star, that's the importance of each feature, like I said. I'm using P to mean the set of all pairs of items, and then S sub M are our samples. So they have a pair and a label, and that label is the outcome, 1 or 0, depending on whether I is preferred to J. Okay. So how do we get that outcome? We use the Bradley-Terry-Luce model, except we introduce a new idea, which is this selection function. Okay, so tau takes a pair of items and maps it to some subset of the d coordinates. Okay, and I'm going to call it the selection function. So in this picture, if tau takes the fuzzy boot and the loafer, it will map to the 2nd and 5th coordinate. And then when we're going to use this notation that u superscript tau restricts u to those coordinates. Okay. And for each pair, obviously, then we can get a different set of coordinates. So this selection function takes in the pair and outputs the set of coordinates. So using this selection function, how do we get the outcome of the pairwise comparison? We have a logistic function that's based on the utility of each item, but that utility is a utility in context. Okay, so the utility of the item is dependent on this selection function, and it only looks at the coordinates of the feature based on that selection function. And the items then are ranked by sorting the full feature utility. So that's our assumption that the full ranking comes from, not down selected feature utility. And feature BTL is a special case of our model where the selection function always selects all of the coordinates. Okay, so that's our mathematical model. Given the samples, then we have a negative log likelihood function, which, as I said, is a convex function. And we can minimize to find our estimate for the judgment vector W. Okay, so I just want to stress one more time that what we assume is that we have item features, this U matrix, and actually we also know the selection function, tau. Okay, so that is probably the most major assumption of this work that needs to be overcome. But I'll share with you the one that we started with in our experiments and why we selected that one a little later. Okay. Okay, so the sample complexity theory that we have is based on this maximum likelihood estimate of the parameters W in our model. Okay, W is the judgment weight vector that's unknown. First of all, we asked when is our model identifiable, and we have a result for that. Basically, it says that if you restrict for every pair to the coordinates of the selection function and take the difference between those restricted feature vectors, after collecting all of them over all the pairs, it should span the whole d-dimensional space, okay? And this is, you know, very intuitive. As an obvious example, if there's any feature that is never used in any of the comparisons, then that coordinate of W star can't be learned, even if there are infinite data. Okay, so first we had our identifiability result, and now I want to share the sample complexity. In order to do that, I have to define 3 terms. All of them depend on this pairwise difference of feature vectors, okay, or the utility difference between the 2 items. So the first one, B star, is the maximum absolute difference between the pairwise utilities, okay? So W star with each one of these vectors gives the utility of that pair in context. Lambda is a minimum eigenvalue of a matrix here. And that matrix is the outer product of this difference of feature vectors, okay? So if we look at that expected matrix, then the minimum eigenvalue should be, well, you'll see on the next page, it should be strictly non-zero, okay? And finally, I have this term beta, which is the maximum coordinate-wise difference of these feature vectors in context. Okay, so given these 3 parameters, I have this following sample complexity guarantee. So W hat is the maximum likelihood estimator of our judgment vector. And we have a probability parameter delta. If lambda is strictly positive, and we have some number of samples m, which is lower bounded here, then with probability 1 minus delta, we can get the following upper bound on the error between W star and W hat. Okay. So we have an exponential dependence on B star, lambda in the denominator, and then our number of samples is in the denominator underneath this square root, and above it you see is something on the order of d log d, or b squared d log d. Sorry, beta squared d log d. Okay, so let's try to interpret this a little bit. First, like I said, lambda is equal to this minimum eigenvalue, and it's actually another necessary and sufficient condition for identifiability. So, so it's equivalent to that earlier condition that I shared with you. Exponential dependence on B star is found in all of the different analysis for like estimating these W star vectors. It's not, no one knows really, is it absolutely required, but it is somewhat intuitive because B star is large when the logistic function has, so when you have like some utilities that are very, probabilities that are very close to 1. And we know in the logistic function, it's very hard to learn differences when you have, you know, probabilities that are extremely close to 1. And so then it would be hard to learn the judgment weights in that case. Exponentially hard, I'm not sure, but it's comes in through the proof. And finally, just to give kind of a nice interpretation. So if we took all 3 of these parameters that I defined earlier to be constant, then you'll see that we need about d log d observations to control this error. And then if we increased it, let's say to you know, some constant more, or d log square d, then we can get this error to go to 0. We have several corollaries of this theorem. So I'll just tell you what they are at a high level, and anyone can ask later or if they have specific questions. So the first one is sample complexity for full feature BTL. So in that case, then, you know, the selection function is just selecting all of the features. And actually, is to the best of our knowledge, this was the first time this was presented in the literature. Okay, and the interesting interpretation of this corollary is that we only need d log d samples to control the error, but existing results for BTL without features require d squared log d, okay? And so it kind of says that having features actually helps you do your prediction. It makes sense because, you know, assuming that features exist and are the way that we make these comparisons is a somewhat strong assumption. We have another corollary that analyzes the sample complexity when the function selects just one coordinate for every pair. And this one, the conclusion is basically that if there's a coordinate that is not often selected by tau, then it takes a lot more samples to estimate W star. And sensibly, it would require a lot of samples just to estimate that coordinate that wasn't selected. But if every coordinate is selected about the same number of times, then it says we need d squared log d samples, where, you know, in each one, we only use one coordinate for the feature comparison, for the pairwise comparison. Okay, so our last corollary analyzes the complexity for going to a universal ranking. So I'm going to just go to the empirical results so that I have time here to talk about these. Okay. Okay, so we have two sets of empirical results. One is for synthetic data, and one is for the Zappos data and the district data. Okay, so first I'll just talk about the synthetic data. So first, we wanted to do these synthetic experiments to kind of confirm that our model does produce systematically intransitive preferences, okay? And we wanted to illustrate our sample complexity bound and look at model misspecification. So in this setting, we have feature vectors of length 10 and 100 items for comparison. And we just draw them all as Gaussian. And comparisons are sampled using a specific selection function. Okay, so I mentioned earlier, we have to know the selection function in order to perform the likelihood, the maximum likelihood estimator. And so one particular selection function that is talked about in a lot of the social choice literature is just to say that when people look at a pair, they make decisions based on the features that are the most variable, okay, or basically the farthest apart. So that's exactly the selection function we used for all of our synthetic and real data experiments, was that we look at the top t largest coordinates, or sorry, if we look at the distance between all the coordinates of the two feature vectors, we take the top t largest distances, and those t coordinates are the ones we use for our pairwise comparison. Okay, so, you know, I mentioned the corollaries. For example, the one where the tau selects only one coordinate per vector. You know, in this case, that one coordinate selected would be dependent heavily on the feature vectors themselves. Okay, so analyzing something like that could be complicated, but is of great interest. Okay, so in this first plot, we show as we increase t, so meaning as we take more and more coordinates in order to do the comparison, we see how many of the triplets have a violation of rational choice in some way, okay? So green, orange, and green, blue, and orange are weak, moderate, and strong violations of stochastic transitivity. And then the red curve is pairwise inconsistency. So what does pairwise inconsistency mean? It means the number of pairs that are not consistent with the true full ranking. Okay, so if we had the true ranking and then we have some pairwise probabilities that it looks like A is better than B when in the ranking B is higher than A. Okay, so this selection function clearly does result in intransitivity, the smaller number of features that are selected. And when the whole feature vector is selected, there's no intransitivity. That's the feature BTL model that has been worked on for some time. Okay. In this other plot, we wanted to look at how the estimation error goes down with the number of pairwise comparisons in order to illustrate our sample complexity. So first, just focus on the green line for sample complexity. So in this case, we generated data using a top 3 selection function, and the green line assumes t equals 3. So it uses the right model for learning the model from data. This rate that you see in the green curve is the same rate that we have in our sample complexity. So our sample complexity bound isn't tight. The constants are quite loose actually, but we see that it's exactly the same rate of decay. So we have confidence that the bound is accurate, at least in terms of rate. So now if you look at the other curves, it's more important, or an important other conclusion we wanted to show with this plot was model misspecification. So since we're assuming that we know this selection function from this plot, we can see it's actually pretty sensitive to knowing exactly the selection function, which is important. And so, in this case, even if I use, a different, saying we only use the top 1 feature in terms of differences, or we use all the features, then we get much worse sample complexity as the number of these comparisons increases. Okay. So this is a really key challenge going forward in how to handle that in our data, or sorry, in our model. Here's another plot for doing the same model misspecification, looking at Kendall-Tau correlation. So here it's a little more promising that says if you're only wanting to correlate with the true ranking as opposed to exactly estimating some W star parameter, then actually it does pretty well. But still, even with one of the cases, meaning that you use t equals 1, where you're only selecting 1 feature, the Kendall-Tau correlation is not as good as the other cases. Okay, so that's our synthetic experiments. Then I have a set of 2 experiments with real data, and the first one is from these district data. So the district data actually, they felt when they collected the data, they felt terrible. They had collected all these pairwise comparison data and they felt they weren't useful for anything. So they went and collected all these ranking data. But that was a great data set for us because we can look at pairwise comparisons, try to learn from pairwise comparisons, and then ask if they match the rankings that are gotten by, when people ranked the large sets of districts. Okay. And so that's what we did. We learned on the pairwise comparison data and then looked at the Kendall-Tau correlation to the rankings, okay? So in each one of these columns here, there's a different sub-data set from the district data, okay? So they use, people on certain subsets of the data, and they collected them into these 7 different data sets. And the columns, or sorry, the rows are our method at the top, and then feature BTL ranking, support vector machine, and RankNet, which is a neural net. And though the Kendall-Tau correlations are not very high, you can see that for the salient feature method, they are the highest. And you know, in fact, for some of these, they get something that seems like much more reasonable, 0.6, say. It seems like it's actually lining up a bit with what people were saying in that data set, okay? And it's doing better than most of the other methods across the board. So, you know, that indicates maybe there's some kind of intransitivity, and at least paying attention to it, we can get a little bit of gain. But clearly we haven't exactly been able to model the real data in any of these, using any of these theoretical models. Okay, the second data set we looked at is the Zappos data set, where people compared shoes based on a particular characteristic. So I mentioned comfort earlier, but there were actually 4 different characteristics that they asked about: whether the shoe is open, pointy, sporty, or comfortable. Okay, so within each one of those categories, they asked what they called fine-grained and coarse-grained questions. The coarse grain was like showing a high heel and a tennis shoe, something very different, and it sort of has an obvious answer for comfortable or pointy, say. And fine grain was showing, you know, shoes like flip-flops and loafers that are much closer and harder to discern. So here I show the result in pairwise prediction accuracy for the fine-grained data. So Zappos only collected pairwise comparisons, so we don't have any rankings to look at, but at least we can ask if our pairwise prediction accuracy is as good or better than the other methods. And you'll see from the plot, from the table, the same is true in the coarse grain case, that a salient feature method doesn't do any better than the other methods, but at least it does as well. And one thing that we found very interesting, so the way we trained this was to you know, have a test, a validation, and a training set. And from the test set, we would you know, try our model for some particular T using the top T selection function. And then from the validation set, we selected which selection function is the best, so a hyperparameter selection. And in every case, the T that was chosen by the validation set was always something less than all the features. Okay, so it really shows that you know, using all the features, it gives you worse error on a validation set. So there's a lot of redundancy, and some kind of sparsity model is appropriate for these data. Okay, so that concludes the empirical results. And just to say what we like to do going forward. So I think I kind of stressed that the biggest assumption we made was that we know what this selection function is, and that we have features given for every item. And so something that we're very much interested in is trying to learn that selection function from the data. Of course, our model won't be convex anymore, but it could be you know, still possible given the framework that we set up here. We'd also like to extend this framework to other types of ordinal comparisons, so like not just pairwise, but higher order k-wise comparisons, or other types of triple comparisons, like is A closer to B or is C closer to B? And then lastly, we're very interested in understanding how does intransitivity you know, change the sample complexity. And when we started this project, we thought, you know, for sure, the more intransitivity there is in the data, the harder it would be to learn the model from data. But it didn't look exactly true when we were doing our synthetic experiments. So we're trying to still sort of tease out, you know, how does intransitivity in the data really affect however many samples you need in order to learn a model that does a good job at predicting pairwise comparisons or rankings. Okay, so that concludes the talk. You can find our paper on the archive or listen for Amanda's talk at ICML, and I can share my slides, and here I have all the references that I mentioned throughout. So thank you for your attention, and I'd be happy to take questions if there's time. Sorry, I noticed it's already 9, but if there's time, I'm happy to take questions.
Thank you so much, Professor Laura, for this really interesting presentation. So now we have times for some questions. So once again, if you want to ask any questions, you can go to the participants menu, and then you'll have a raise hand button on the bottom right. I will ask you to unmute, and then you can unmute your mic and talk. So you can also ask questions through the chat if you prefer. So are there any questions? Okay, we have a question. So it's the usual. Okay, I think you can talk, Mario.
Yes, Laura, thanks for the great talk. We have discussed these a few times, so kind of maybe I could ask some insider questions. I'll try not to. So when all this seems to hinge very critically on the selection function.
Yeah.
And you mentioned at the future work slide that's one of the research directions. Do you have any ideas? Can you say a little something more about what you find as promising directions to work in that for that goal?
Yeah. So the first direction that we were hopeful about is just using sparsity regularizers. So, we can say that there is some selection function and we don't know what it is, but that it's sparse, that it chooses some small number of coordinates for every pair. There's a challenge in that if the number or if the set of coordinates is different for every pair, then we actually have a very large matrix that we need to estimate, even though it's sparse. So if that matrix, it turns out, has it's a very, very large matrix. It's mostly 0, but wherever there are non-zeros, the whole row should take the same value. And so we've been trying to investigate other regularizers, so not just sparsity, but ones that also sort of force the non-zero values to take the same value. And we're hopeful that that can help alleviate the increased sample complexity needs because of this large sparse matrix that we're trying to learn. Another thing that I would be very interested in, but I don't really have ideas yet, is if we allow that selection function not to be a sparse or a coordinate selection function, but to be any projection, any lower dimensional projection. So in that case, then we would be able to say, take some linear combination of the entries of the features. And what's interesting to me in that case is that then, in some sense, we're learning which features are important and in what combination. So it may be not that the center of mass to the farthest point is the feature, and it may not be the convexity, but it may be some combination of those features that's the sort of true mental feature that we're using when we're making the comparisons. So those are just 2 possibilities of future directions there.
Thank you.
Yeah.
So thank you for your question. Are there any other questions? Okay, so once again, thank you so much for your presentation, Professor Laura. It was a really interesting topic.
Great.
So this is it for today. This was the last seminar of the season. Thank you for being present today and throughout the last months. And thank you for continuing to attend the seminars even when we went remote and lunch was no longer a bonus. So thank you, Professor Laura, and thank you all for staying with us.
Thank you so much for the invitation.
Of course. And so I hope to see you all again next year. Thank you again and keep safe.
Bye.
Goodbye.